Yes. Okay, guys, we should be pretty much timing out on the quiz at this point. So hopefully everybody can see my whiteboard okay. I'm actually operating off one screen today. I'm in at the university instead of from home. So I'm kind of just going back and forth between screens here. I was kind of watching the progress on that quiz there, and it looked like the one that most folks were struggling with was the one where you had to generate the equation from the names of things. Okay, so make sure that you're practicing that, because that kind of goes back to stuff that we did a couple weeks ago, maybe 3 weeks ago or 2 weeks ago or something like that, where we were actually learning how to go between names and formulas. So that's something you definitely want to keep track of, and remember that whatever we learned in the past is still kind of fair game. So you still need to remember how to do that, and that's where the practicing will help. So there's bunches of those there in Chem 101 you can work on in the homework that we've got. There were a couple that were on the practice last time, but I'm not sure that many folks got to them. But make sure you're looking at those so you remember how to do that. Okay, so what I want to do today is I want to keep working with limiting reactant. And I want to kind of pull stuff together here and build on what we talked about in last night's video. And essentially go through a problem that will let you see everything and anything that you have to know about working a limiting reactant problem. So basically, in this kind of problem, I will show you anything and everything you could ever be asked, okay? And probably anything you didn't want to know too. So this is a nice comprehensive problem. So let's kind of lay it out here. So I'll just put this down as limiting reactant so you have a topic here. All right, so let's define an equation here. That's usually what happens. I'm just going to give it to you as a balanced reaction equation. Presumably you guys are okay at balancing now, or you could go back and verify it if you wish. 4NH3, that's ammonia, it's a gas, plus 5 oxygens, also a gas. And what we're going to make is 4 NOs, which is nitrogen monoxide, that's a gas, and 6 waters. And that's a gas. Okay, so this is a gas phase reaction, so presumably it's being done at a higher temperature so the water doesn't actually condense into the liquid state. So here's the situation. We're doing this, for example, in a closed container like we talked about in the video, and we're starting out with 25.0, and I'll just go ahead and put the amounts down here, grams of the ammonia gas. As far as the oxygen goes, I'm going to also put into the container 45 grams of the oxygen gas. And we don't know anything about the products. Now, it turns out the product that we're going to focus on is going to be the nitrogen monoxide. In other words, that's going to be the product of interest. So basically, we're ultimately going to want to find out how many grams of that we've got. Now, the other thing, since we're going to go between grams and moles, that I'm just going to throw in here for you, just so we can refer to them instead of calculate them, are your molar masses. Okay, so for ammonia, if you go to the periodic table, you'll find out that's 17.031 grams per mole. And the oxygen, you guys have used this one before, that's 32 grams per mole. And your nitrogen monoxide is 30.01 grams per mole. Okay, so there's all the information that we're going to need in the problem. So now we have to decide what it is we're trying to get. Okay, so if you look at the problem in terms of how I set it up here, we know something about both reactants, right? We have initial masses of those. All right, but what we want to find out about ultimately is what the theoretical yield of the nitrogen monoxide product is going to be. In other words, how many grams of it can I make based upon the limiting reactant calculation? So to do that, I need to first figure out what the limiting reactant is. Okay, so that's going to be my first part of the problem. So I'm just going to put limiting reactant here. So we know what we're trying to get. Okay, now in the video, I showed you a couple different ways of doing this. I showed you the situation where we could compare reactant to reactant and figure out which one of them we have less of, or I can take each one directly to the desired product and then figure out which one gives me less product, and that one would be the limiting reactant. Now I'm going to do the reactant to reactant mode here, and I'll show you why when we get to the next part of the problem. But you can do it just as well by just taking each reactant onto the desired product. So it's kind of up to you in terms of which way you want to go with that. But we'll do the reactant to reactant comparison method here. That was the first one we talked about in the video. So I'm just going to start out with the ammonia. So we're going to start out with the mass of it we've got. That's 25.0 grams of NH3. And we always take it directly to moles first, right? We always go from grams to moles before we do anything else. And since I picked the ammonia first, I just want to find out how much of I've got in terms of moles. So I'm going to use my molar mass here. I've got 1 mole of NH3, and that corresponds to 17.031 grams of it. And that takes me to moles of ammonia. So to my 3 sig figs, that is 1.47 moles of NH3. Now, when you look at that, that's telling me how many moles of NH3 I have available to me. So I'm going to put have there. Now, in the next part of this, if I'm going to do a comparison, I can work from the standpoint of the oxygen that I have, and then figure out how many moles of ammonia I'm going to need to react with all the oxygen I've got. Then I can make a comparison between what I have and what I need, and then determine a limiting reactant based on that. Okay, so focusing on the oxygen now, I've got 45 grams of that. Take it to moles. We always do that first. So we know that 1 mole of oxygen gas corresponds to a mass of 32 grams of it. Okay, but now what I can do is I can use my mole bridge, right? Because I want to take this back to ammonia and find out how much ammonia I'm going to need to react with all of that oxygen. So I can establish a mole ratio based on that mole bridge, in this case, between oxygen and ammonia. Okay, so that's what's going to happen next. And that's so I can compare apples and apples, right? I want to compare ammonia to ammonia. So it looks like moles of O2 have to go in the bottom and moles of NH3 have to go in the top. Now I can establish my mole ratio. Looks like for every 4 moles of NH3, I'm going to use 5 moles of O2. Everybody see where that came from? Okay, so now just checking our units, grams of O2 cancel, moles O2 cancel, I'm left with moles of NH3. And to my 3 sig figs, I get 1.13 moles of NH3. And that's what I need, okay? That's the number of moles of NH3 I need to react with all of the oxygen present. So, do I have more than I need, or do I need more than I have? What do you guys think?
More than you need.
Yeah, I've got 1.47 moles of it available to me, but I only need 1.13 moles of it. So what does that tell me about NH3? Is it limiting or excess? What do you guys think? If I have more of it than I need, is it limiting me or excess?
Excess.
Excess.
Excellent. Very good. Okay, so by default, what does that make oxygen?
Limiting.
Limiting. I'm going to run out of the oxygen first. And you know, you could have done the same calculation from the standpoint of the oxygen and then compared oxygen to oxygen, and you would have come up with oxygen as the limiting reactant. So it doesn't matter which reactant you pick. It's just that you have to compare apples and apples. So you compare ammonia to ammonia or oxygen to oxygen. You pick and you'll get the same answer either way. All right, now why do we need the limiting reactant? Well, we need the limiting reactant because ultimately that's going to, going back to our balanced equation, dictate how much of the nitrogen monoxide I'm going to make, because once I run out of the O2, I can't make any more of the NO, right? So that's why I have to do the limiting reactant first. So now what I want to do at this point is figure out the theoretical yield. In other words, how much of the nitrogen monoxide can I make based on the limiting reactant that I have? Okay, so we basically said that the oxygen was the limiting reactant. So we're going to just work backwards from the standpoint of the oxygen. So I'm going to go ahead and just start with my 45.0 grams of O2. I don't have this calculation anywhere else, so I'm going to go ahead and just work it. Take it to moles. So 1 mole of O2 we said was what, 32 grams of it. Okay, now I need a new mole bridge, don't I? So let's go back up to the balanced chemical reaction equation here. Now I need to go from the O2, which is my limiting reactant, back to the NO, don't I? So I have a new mole bridge here I can use. Okay, so let's establish a mole ratio based on that mole bridge. Moles of O2 have to go in the bottom. So I want to get rid of them. I want to keep moles of NO, that's going to be on the top. And if you go back to that balanced reaction equation, you'll see that for every 4 moles of the nitrogen monoxide you make, you're going to use up 5 moles of the O2. We'll just go back and verify that real quick. Yep, 4 moles of NO to 5 moles of O2. All right, but I want to go to mass, don't I? It's ultimately mass of the NO that I want. So now I just need the molar mass of the NO, which I think I gave you in the problem. So for every 1 mole of nitrogen monoxide, I got a mass of what, 30.01, I think I gave you in the problem, grams of NO, okay? So that should take us where we need to be. Let's just double check. Grams of O2, cancel with grams of O2, moles of O2 with moles of O2, moles of NO with moles of NO. I'm left with grams of NO. That's what I want. Looks like I'm going to be good to 3 sig figs there. And when I work it out, I get 33.8 grams of my NO or nitrogen monoxide that I'm going to make. Okay. So again, that's based on the limiting reactant. In other words, the reactant I'm going to run out of first. That's what's going to dictate how much product I can ultimately make. Okay, so that's pretty much everything we did in the video, just applied to a different problem. Any questions at this point before I go on? Because we're going to do some other stuff as well. Okay, good.
So that 30
Yeah.
is the molar mass of NO, right?
Yes.
Okay.
Yeah, that 30.01, and that was given in the problem. If you go back up there, see it there under NO at the top. And you could have figured that out from the periodic table if you needed to. I just put them in there because it just saves us some time in the problem. You guys know how to calculate molar masses. All right, so the next thing I want to find out is I want to go ahead.
Could we use the 1 point? Could we 3 moles of NH3 that we calculated in the limiting reaction to just skip terms of the equation we used to find the theoretical yield?
So in other words, could you use the need part? So yeah, you could probably do that where you've got the 1.13 moles of NH3 that you need. So that's going to tell you how much of it you're going to use up based on the limiting reactant. So yeah, you could establish a new mole bridge if you wanted to that way. So in that case, if you know how much NH3 you're going to use, which you do, you could do another mole bridge from the NH3 over to the NO if you wanted. That should give you the same answer theoretically. So yeah, there's lots of different ways you can work the problem. As long as you knew how much NH3 you actually used in the reaction, that would be fine. But the problem is that many students will go back and use the initial amount, which is not correct because then you'll end up making more NO than you should. So be careful when you do that, that you're using the correct value. But yes, you could do that. All right, so the next thing I want to find is I want to find the grams of excess reactant. Okay, and we said the excess reactant was what, the NH3? So in other words, I want to know how much NH3 is left over at the end of the reaction. Okay, now here's the advantage of working the problem out the way I did in terms of looking at a mole-to-mole relationship between the reactants, is now, notice what I've got up here. I'm going to put little check marks over it. I've got the 1.47 moles of NH3 that I have available to me. And I also have the 1.13 moles of NH3 that I need to react with all of the O2. So is there a way that I could get the number of moles of NH3 that are left over after the reaction from those two values as I have them? How would I do that? It's actually really simple.
You find the difference?
Yeah, you just take the difference between them. You take what you've got and subtract from it the amount you actually used up, which is the amount you need. Okay, so that's what I'm going to do. And that's the advantage. You don't have to introduce any different mole bridges or anything like that because you've already done the work up top for that. Okay, so I'm going to take the 1.47 moles of NH3 that I have. I'll put have underneath so we remember that. And subtract the amount that we actually used, which is what, the 1.13 did I say? That's what actually got used because it's what we needed, right? And to my sig figs, I will end up getting 0.34 moles of my NH3. That's what I've got left over. Okay. So in other words, it's the amount of excess of my excess. Now I want to take it to grams, but that's easy because I got moles, right? So just in a separate step because I'm out of room here. 0.34 moles of NH3. And now I can just use the molar mass to take me back to grams, can't I? So for 1 mole of NH3, it looks like I've got, what, 17.031 from up top. Grams of NH3 is my molar mass. So moles will cancel with moles. I'm left with grams, and I end up with 5.8 grams left. Okay, so that's something else that you sometimes get asked in a problem like this is determine not only what your limiting reactant and your excess reactant is, but determine how much of your excess reactant you've got left over after the fact. Okay, so you always have to get the amount of each reactant, okay, and then do a limiting reactant calculation and then find out your excess. And then based on the difference in the moles of the excess, you can get back to the grams of the excess. Okay, so that's how we would work that type of problem. Now, there's one other thing that we could ask you about. It's introducing a new definition for you, and it's a definition that's often used in the synthetic lab or actually in any kind of a scale-up synthesis lab, where we actually worry about how much product we actually make. And that's something called the percent yield. So like in the lab, and I think you guys do a little synthesis lab in bonding, where you actually end up measuring a percent yield. And here's what it is. Percent yield is going to be the ratio of the grams of the product of interest that you actually make divided by the theoretical yield, which is also in grams. That's what we just calculated, right? It's how much we should make. And then since it's percent, we're just going to multiply it by 100% to make that work. Now you might ask yourself, well, why would I have to do this? I mean, why would there be a situation where we don't actually make exactly what we think we're going to make? And it turns out in the real chemistry world, there are probably 20 different reasons why you don't make exactly what you think you're going to make. Okay. For example, we'll find out later on, if for you guys who take dynamics, that reactions really don't go 100% to the right. We actually end up having to apply equilibrium to reactions, and we end up actually for any reaction with a distribution of reactants and products. So that's one reason. Another reason is that you could have side reactions that take place, so that you end up making other products from your reactants that you didn't know about, and that actually ends up decreasing your yield. You could lose some of your product when you're trying to isolate it and purify it. So there's lots of different reasons why your percent yield is not going to be 100%, which is what we would think it would be. So in our problem, let's just go ahead and say we ran the reaction. And let's say that when we actually ran the reaction, we really collected 31.5, I'm just making a number up here, grams of nitrogen monoxide. Sorry, I already had the grams there. Okay, so now I want to calculate the percent yield. Okay, so the percent yield for the reaction, when we actually ran it, is the ratio of what we actually got, which is 31.5 grams of the NO, divided by what the limiting reactant calculation said we should have gotten. So we can go back up to that, and there it is. There's our theoretical yield. It's 33.8 grams of NO. And then we'll turn that into a percent. And it looks like we're going to be good to 3 sig figs, and I get 93.2%. Okay, and that's actually in the real world a very high percent yield. In many synthetic reactions, you're lucky if you get 50%. Okay, but that's how we calculate it. So the other piece of information we need is actually an experimental number based on somebody going out and actually running the reaction under a certain set of conditions, and then measuring the real amount of the product that you got, and then comparing that to what the limiting reactant calculation says you should have gotten. Okay, so pretty much there in that problem, guys, that's everything we could possibly do with a limiting reactant calculation. Okay, so you've seen it all at this point. The only other thing that I think comes up, and you'll see it in lab if I remember correctly, it's been a long time since I taught that lab, but I think there's one there where you do it and you end up with 3 reactants, okay? And you have to determine out of the 3 reactants instead of 2, which is your limiting reactant. So think about that. How would you guys do that? How would you calculate a limiting reactant if you got 3 reactants instead of 2? I mean, what would be the easiest way to do it? Well, I would just take each reactant, run it to product, and see which one gives me the least amount of product, right? And that one's got to be the limiting reactant. That's how I would do that. But if you wanted to do, for example, the comparison between reactants like we did in this problem, you'd have to do it kind of like a round robin deal, right? You know, a series of eliminations, if you will, you know, kind of like a NCAA tournament or something, like a b-ball tournament. So what you'd have to do in the case like that is just pick 2 reactants and make the comparison, and then you eliminate one that happens to be the excess reactant. Then you take the one that's still alive, right? And then you compare it to the 3rd reactant and see which one is limiting. So either way will get you there, but just be aware that that can pop up as well. And you do actually have a lab where that does pop up. All right, any other questions about that before I leave it, guys? Everybody good? Okay, let's pop back over to Chem 101 for a little bit and see what we got over there. I believe I have a limiting reactant one here. So let's just see how far we go with this here, guys. It looks like it's about 15, 16 minutes. So should be just about the right amount of time. Looks like you got 4 problems there. Kind of take a look at them here. And again, don't worry if you don't get them all done. Just kind of pick 1 or 2 and see how it goes. And pay attention that some of the reactions run balanced, so you have to check that before you go. I see most of you guys are working on number one, but they don't really tell you in there how much of the H2O you've got, but they do tell you how many moles of NO2 do you have there. So in a situation like that, what do you have to assume? All right, guys, we're down to about the last minute or two of class here. Feel free to continue working. You do have a few more minutes if you want. Progress is good on these, by the way. You guys are doing well with this. Keep in mind, we're starting into some new material, new video for Monday. So I think that's going to be starting into types of reactions. I think we're going to be looking at precipitation reactions. Make sure you watch that and be ready for a little 5 for 5 quiz. And you may see a problem very similar to one of these on it. All right. Any other comments or questions, guys? All right. If that's the case, you guys have a wonderful weekend. And we'll see you on Monday.